Chemical reactions. In a chemical reaction, one or more substances are converted into one or more different substances. Chemical reactions are chemical changes. It's like building things with Legos. You take the Lego structure apart and you put the Legos together in a different way. You've made a new Lego creation, but the atoms, the Lego bricks, are not changed. So the atoms are like Legos. They don't get changed in a regular chemical reaction. They just get rearranged and combined in different ways. A chemical equation is just a description of the reaction. It's like a shorthand. It's a little bit like a math equation. We've got reactants on the left side and an arrow that points to the products. The reactants react to produce the products. The equations give us a lot of information. They can give us the formulas and the states of reactants and products, the relative numbers of reactant and product molecules that are consumed and produced, and they can be used to help us find the masses of reactants used in products made. In a chemical reaction, and you want to end up with 1 kilogram of product, the equation is what's going to allow you to figure out what masses of reactants you need to start with. Some symbols that we use to indicate physical states for the substances in a chemical reaction. Just letters inside parentheses immediately following the formula for the compound. G for gas, L for liquid, S for solid, and we already mentioned AQ means aqueous. That just means it's dissolved in water. The combustion of methane produces carbon dioxide gas and gaseous water. So whenever something burns, it's going to combine with oxygen. And we should recognize this because how do we put out a flame? Well, you can squirt water on it. Why does water put out a flame? Because it keeps the air, which contains oxygen, from the flame. Have you ever seen a candle snuffer? It's just a little upside down cup on a stick, and you hold it over the flame, and the flame goes out. It's like magic. What happened? Well, it confines the flame to this small area and restricts the flow of fresh air in. The candle burns up all the air, and the flame goes out. If you have a small votive candle burning on the table, and you take a dinner glass that's empty and tip it upside down and set it over the candle. It'll burn for a little while till it uses up all the oxygen and the flame goes out, because things don't burn without oxygen. So anytime we have something burning, remember there's got to be oxygen involved. So here is an equation for the combustion of methane. Methane is CH4. We have not learned that, so don't worry about it. Methane in the gas state reacting with oxygen to form carbon dioxide and water, and both of these are gases. But there's an issue here. On the left side are the reactants. Every atom that's present in the reactants must be present in the products, and vice versa. We can't have atoms appearing out of nowhere. We can't have them disappearing or changing into other things. In the reactants, we have 2 oxygen atoms, but over here in the products, we've got 2 oxygen atoms here and 1 oxygen atom there. Where did the extra oxygen atom come from? Well, our description, our equation is wrong, is what the problem is. The other thing that's wrong with that equation is there are 4 hydrogens on the left side of the arrow and only 2 on the right side. What happened to those 2 hydrogens? Did they turn into an oxygen atom? No, they can't do that. Red Lego bricks don't change into blue ones. Doesn't happen. A chemical equation is not unlike a math equation. You can think of the arrow as being like an equal sign. And however many C's, H's, and O's are on the left side of the equal sign have to be the same as the ones on the right. This equation is violating the law of conservation of mass. So what we do is we balance the equation. And we do that by changing the coefficients, the numbers of molecules, not by changing how many atoms are in the molecules. So here we have pictures. The pictures are real helpful. Here's methane. It's a black ball with 4 white balls on it. And it's really, if we give it another oxygen atom, that's going to help things out. And then over here, CO2 is a black and 2 reds, and water are familiar little Mickey Mouse heads, red with 2 white balls. There's got to be 2 of these. When we make 2 of these guys and 2 of those, then we can see there's 4 white balls on that side and 4 on this side. There's 1 black ball on each side. There are 4 red balls on the left side and 4 red balls on the right side. That's what we're doing when we're balancing equations. So that's the picture. We're going to learn that we look at the chemical equation and balance it. We see we had 1 carbon here and 1 carbon there. That was good. But we had 4 hydrogens here, and there were only 2 over there. So we put a big number 2 in front of the formula for water. We don't change the formula for water. It's tempting sometimes. Yeah, but if I made it H4O, it would be good. You can't do that. But you can put a 2 in front and say, well, there's 2 water molecules. And so then there's 4 hydrogens there and 4 here. And then over here we had 2 oxygens, and now we have 2 oxygens there, but we only had 2 over here, so we need to put a number 2 in front of that. And now we end up with 1 carbon, 4 hydrogens, 4 oxygens on each side of that arrow. Any questions? Another list of directions how to balance chemical equations. You start with a skeletal equation, your formulas for the reactants and products. The formulas need to be correct. Then we balance it, and we call this method balancing by inspection. So they're going to give you a couple guidelines here. Balance the atoms that occur in more complex substances first. Always balance atoms in compounds before atoms in pure elements. And then balance atoms that occur as free elements last. Those are suggestions meant to help you do it in an easier way. There are easier ways and harder ways to accomplish the same thing. The easy way for me to get home to Reedley is to take 99 in Manning. The hard way for me to get home to Reedley would be to go north and drive all the way around the earth. That would be really hard, right? Could I get to Reedley by going north? Yes, eventually I could.
Why not take the 180?
Well, I could take the 180, and that's a pretty easy way too. It just kind of depends. I've had some bad luck coming here that way because I get behind some slow trucks, and they cannot be passed. Trucks that cannot be passed. Very frustrating. But that's definitely easier than driving around the world. But there's different ways. And as long as you get to your final destination, that's great. But let's try to pick an easy way. And so that's all that number 2 and 3 here are doing. We're going to balance these things by using coefficients. We cannot change the formulas. And then once we get it balanced, we're going to look at those coefficients. If we have any that are fractions, we need to clear them out. And we want to have those coefficients be the lowest whole number ratio of molecules. And then double check. So let's do a couple examples. Within the cylinders of a car's engine, the hydrocarbon octane, C8H8, one of the many components of gasoline, mixes with oxygen from the air and burns to form carbon dioxide and water vapor. Write a balanced chemical equation for this reaction. So we have learned nomenclature now, right? We can look at these words and identify the formulas for them. So there is a chemical reaction, a chemical equation hiding in this paragraph. And sometimes it's harder to pick out than others. So the hydrocarbon, that's an adjective, octane. Octane mixes with oxygen and burns to form carbon dioxide and water vapor. So there's our ingredients in there. So we're given the formula for octane, C8H8, mixes with oxygen. What's the formula for oxygen? O2, very good. Actually, I want to leave a little more space there. Leave some space for coefficients. To form, what's the formula for carbon dioxide? CO2 and H2O, water. So there we have the formulas for the reactants and the products. We need a balanced chemical equation. So I'm going to show you one technique that seems to work well for a lot of students. Other students say, well, that's an awful lot of work. That's kind of overkill. It's okay. So we've got three elements here. We have carbon, hydrogen, and oxygen. And I'm just going to kind of tally up what I have going on below the equation. And I'm going to draw a line where the arrow is, because that's what we need to balance, what's on the left side of the arrow and what's on the right side of the arrow. I'm just going to go across, and here's my first compound, C8H8. Well, that's got 8 carbon atoms and 8 hydrogen atoms and no oxygen atoms. And then I've got O2, and that's got 2 oxygen atoms and no carbons or hydrogens. So just kind of keeping track of what's out here. On the right side of the arrow, there's 1 carbon and 2 oxygens in CO2. There's 2 hydrogens and 1 oxygen in H2O. It's a little easier to see when you actually have some lines. I don't know if I can actually make lines here. They start to waver all over the place. Maybe that's a little better. Occasionally, you'll get an equation that's just balanced out by itself without any coefficients. Those usually are not assigned as homework problems. So to see if this is balanced, we're going to look first at carbon. Why? Because it came up first. If you start balancing an equation and it feels like you're going around in circles and you keep changing elements and elements, just stop and start with a different element. The guideline was to leave elements for the last, so we're going to leave oxygen for last because he's all by himself. But here we've got 8 carbons, and over on this side we only have 1. We can't take carbons away from this side, but we can give carbons over here. So we're going to put a coefficient of 8 in front of this. 8 CO2. That's going to give us 8 carbons. It's also going to change the number of oxygens and give us 16. Now the carbons are balanced. Hydrogens on the left, there's 8 of them. On the right, there's only 2. Well, we can fix that by putting a 4 in front of water. And that will change the 2 into an 8. It'll change the 1 into a 4. We're just multiplying. Carbon and hydrogen are great. Oxygen. On the left side, we have 2 oxygens. On the right, we have 16 plus 4, which is 20. So we need to put a 10 over here. And by saving that for last, when we put a coefficient on that one, we don't mess up something we've already fixed, because that can happen. So there's our balanced equation. Any questions? In the destruction of marble statuary, like we saw earlier, by acid rain, aqueous nitric acid reacts with calcium carbonate to form carbon dioxide, water, and aqueous calcium nitrate. Write a balanced chemical equation. Oh, there's a typo I didn't see before. For this reaction. And through the magic of computers, the typo is fixed. So the first thing we do to write the balanced chemical equation is we need the formulas, right? So nitric acid, I'm going to do some little scribblings way up at the top here. Is that an oxyacid or a binary acid? It's an oxyacid. The binary acids start with the prefix hydro. So nitric comes from nitrate. Nitrate is NO3 minus. And that gets with a hydrogen, and so we've got HNO3, nitric acid. Let's practice our state symbols, the little parentheses guys. What's the state symbol for aqueous nitric acid? AQ. Reacts with calcium carbonate. Calcium is a metal, so this is ionic. Carbonate is CO3, 2 minus. Once you begin to master chemistry, you may not actually write this down, but that's what I see in my mind's eye when I see calcium carbonate. Calcium 2 plus, carbonate 2 minus, one of each, CaCO3. What do you suppose the state of that is? That'd be a solid. Marble is largely calcium carbonate. Are marble statues gases at room temperature? No, they're solids, right? So there's a solid. So those two things react to form, there's our arrow, carbon dioxide. Okay, we've seen that one already. What's the state of carbon dioxide at room temperature? It's a gas. I'm getting a little too small here. CO2, gas. And water. We don't have a temperature or anything specified, so if we need to write state symbols, we would assume room temperature then. At room temperature, water is a liquid. If you've got a situation where something's burning, then you can assume that it's hot, right? And aqueous calcium nitrate. Calcium nitrate is going to be the calcium ion and the nitrate ion together. So CaNO3, 2. Aqueous, because they told us that. It got smaller and smaller and smaller, and I still ran out of room. And we need to balance it. So we're going to, instead of doing all those tally marks and things, we're just going to look at this. Over here, I have hydrogen. On the left side of the arrow, hydrogen only appears right here, and there's one of them. How many hydrogens are on the right side? 2. There's H2O. So I've got 2 there. So if I put a 2 in front of HNO3, I'll have 2 hydrogens on each side. Now look what's going on with nitrate. There's NO3, and NO3 shows up over here. The polyatomic ion actually stayed together. And when that happens, you can balance it as a unit. Or you can look at the individual elements, nitrogen and oxygen. let's do them individually this time. So nitrogens on the left, I have 2 nitric acid molecules. So 2 nitrogens here. How many nitrogens on the right side? 2. This nitrate has a 2 on the outside, and so there's 2 nitrogens there. So he's good. Oxygen, I'm just starting at the left here going HNO. There's oxygen everywhere. I'm going to skip him for now, because what often happens is the last one kind of takes care of itself. So I'm going to leave him alone for now. Look at calcium. 1 calcium on the left, 1 calcium on the right. Well, that's convenient. Carbon, 1 carbon here, 1 carbon there. Now we have to go deal with the oxygens. There are so many oxygens, I might want to write down what's going on with oxygen. So here I've got 6 oxygens, 2 times 3. And here I've got 6 oxygens. No, 3 oxygens. Right? CO3, duh. So that's a total of 9. And then over here I've got 2 and 1. And how many in the calcium nitrate? 6. Yay! Exactly what I was thinking. Yay, it worked out. So that's balanced. I only needed 1 number. It can happen. Now, if we got to doing all of this and the oxygens didn't work out, all the other elements were balanced and the last one wasn't, and anything we change is going to mess up the other ones. Occasionally you'll get an equation, you're like, I could go around in circles all day. This is never going to balance. There's usually a reason for that. You got one of your formulas wrong. If you get a formula wrong, you won't be able to balance the equation. So if it seems impossible, double check your formulas. Okay, you need to be able to write the formula for carbon dioxide and for nitric acid. But if you're practicing balancing equations and it's not working out right, Google the formula for nitric acid. Make sure you did it right. Okay?